Back again with another video, guys. In this video I'm going to show you how we would improve the code that we did before. We used the previous program to find out the prime factors of a given number using this method. We have coded this before. Now the problem lies in here is that it runs in time complexity of big O n square. So if the sample space or if the number happens to be large, then it will be difficult for this program to run this, and it would take a lot of time to calculate the given output. So in order to reduce the time complexity of that particular thing down to big O notation O n or less than big O n, we would have to use the alternate method which would improve this program further. So, little bit of information about Big O notation. It is just a tool used to describe the time complexity of an algorithm. So, for example, like if I would give in this input, let me run this. This is the program we did before. We used it to find the prime factors, and if we run this to find the prime factor of this number, it is taking a lot of time. It is 5 digit only. Yeah, it took some time. But when we compare it to using the method which I'm about to show you right now is going to take way less than, and this is how we are going to improve this program. So without any further ado, let's just jump right into the coding. First thing, what I need to do is, this is the problem, and this function is used to calculate the prime numbers up to the number itself, and this is the factors where the number is divisible by. Okay, first we have to find out the number of the prime uh, factors, and we'll see if the prime factors are divisible by the number or not, if the factors can divide the number or not, and that's what this function is doing. And this, we are blindly just trying to find out the prime numbers, then we are making a list, storing them into this list, and after that we are using all those lists to find if the given factors uh, if the uh, if the number is divisible by the given factor or not. If it is, then we will append it to the end of the list, then we'll print out the t, which happens to be this list. Okay, so the problem here is, as you guys can see, this is 1, so big O of n, this is n, right? And over here, if you see, this is n square. After this we got this, right? N square. And this is where the problem lies. So we need to improve this code, and the way I'm going to do is, I'm just going to implement we need to use the library called math. We need to import this. So before we do that, we need to import maths, and that's it. And now the next thing what I need to do is get rid of this code. Okay, it's making things quite complex. It is good when the number of, like, if the number is small, like it would give us the result very fast. But if the number happens to be more than 5 digit, it would take a lot of time to calculate the given output for the given length of the input. So if we see it qualitatively, it is, the program is less efficient. So we need to improve it. We need to make it efficient. So what I need to do is, I'm going to define a while loop, and I'm going to divide this parameter like divisible by 2. If my number is divisible by 2, and then going to equal to 0, then I'm going to append. If it is divisible by 2, I'm going to append 2, right? Because this is the easiest way out, right? Then because, and now I'm going to modify this number as follows, right? Wait. And what it means exactly is going to divide that number by the number 2. We'll reduce it down to the number. For example, number happens to be 8. If it is divisible by 2, then remainder comes out to be 0. Then we need to divide it by 2, then 4, append 2 to 2, right? So like 3 times 2, 8, 2, 2, 2. And now coming back to this, so just use And getting out of this while loop, need to implement this for loop for I in wait, I in range need to start from 3 because we already have defined the criteria for 2. If it is divisible by, if the remainder comes out to be 0, from here we see if the remainder comes out to be 0, then we will append 2 in our list. Then we are going to modify our number by 2, dividing it by 2. Then for condition, if the uh, range from 3 to 3 3 to let's say like, and this is where the main thing, because we would use that library math dot square, right, sqrre, and we're gonna use this library import. That's what we imported it for, right? Make use of it. That would make our program run in time complexity of big O n, and that will reduce the what do we say? That will reduce the time required for the given program to execute, and that's what we are here after. And while x, if the remainder comes out to be 0 for the iteration I, okay, then equal to 0, then what I need to do, I'm going to append that iteration I into my list P, and once we have done that, we are going to modify our x again as follows. And wait, this is what we get, and there is one more condition. If the number happens to be more than the square root, right, square root of this, and if it is not divisible by 2, that is when remainder is not coming out to be 0, and it is greater than square root, the only condition here could be that let's suppose it would always be greater than 2, okay. So there is a condition like if x is greater than 2, what we're going to end up doing is we are simply going to append that number, because it is neither divisible by 2 nor it comes in this range. So it means that it is definitely bigger than this number. If it is bigger than this number, then it is definitely bigger than 2, and whatever that is bigger than this, we're going to append into our list. And p dot append x, and that's what we need. That's what we all need to do. And let's run this and compare it. As we have noticed that it took some time to run before, and now let's see what impacts it's going to have when we modified this much part. Now let's rerun it. Okay, rerun it, and let's just see. The number was 5 digit. Okay, now you see it takes less time. Let's try more digits. Okay, like 1 2 3 3. You can try this. Okay, and remember, it is 1 2 3 4 5 6 7 8 9 10. It is more than 10 digits. Okay, whatever, and it is not even taking that much time. So we have reduced our time complexity from big O n square to big O n. So that is or less, even less than, I think it's less than big O n, because we're taking square root, right? Taking square root. So like it is significantly reduced. I would have to do some analysis to see if it's less than big O of n or it's equal to big O n. So let's just do one more time. Let's just see if it can handle this much. Yeah, let me see. No, it's taking time. Yeah, this is quite bigger. Yeah, it did it. As you guys can see, it did the prime factorization of this number, and it took merely a few seconds. And this is what we can achieve with this kind of code. Earlier we were not able to use this big number, to find out its prime factors, and now we have just used this, incorporated this much part, which has significantly reduced our time complexity, as you guys can see. And hopefully you guys understood this much code, and yeah, I'll catch you in the next one. Stay safe. Bye.